If you have any question, raise your hand or raise your hand, or you can also post it in the chat box. Professor Al-Zubaidi, may I invite you for the lecture entitled to System-Based Engineering Curriculum for the 21st Century Engineering. Professor.
Thank you very much for the introduction. I hope you can see my screen.
Yes, we can see your screen. If you can put it on presentation mode. Perfect.
All right. Thank you very much for the introduction. My presentation for today is entitled System-Based Engineering Curriculum for the 21st Century Engineers. In order to appreciate the pathway forward, one also needs to be first aware of the origin or the starting point. This will be very helpful because if one have enough data from the past to identify a trend and make educated guesses about how that trend is likely to continue, this will, of course, enhance the chances of achieving successful outcome. Therefore, before I outline the structure and the building blocks of the proposed curriculum, I will start with a brief historical look at the engineering profession over time. Let me first start by giving you a short background of this presentation. I first made this presentation 2 months ago at the SME International Mechanical Engineering Education Leadership Summit, MEED. MEED was launched in 1989. It is the only conference specifically for mechanical engineering chairs, deans, department heads that addresses issues affecting the current and future state of engineering education. It brings together educators, industry, government, and ASME representatives to network, foster partnerships, and share ideas for effective educational initiatives to prepare students to enter the workforce post-graduation. However, this presentation is a revised and expanded version that include additional material. This slide shows the branching of engineering through time. It is generally agreed that engineering disciplines were derived from the military engineering to the left side of the slide, which was formalized in the 18th century France through the creation of technical institutes. Inspired by the French Revolution and the so-called Century of Light, the first institute, the École Polytechnique, was established in Paris in 1794. The concurrent Industrial Revolution and the Second Industrial Revolution associated with the rise of the steel, chemical, and electrical industries were driving forces behind the expansion of the Technical Institute or Technical University model that led to establishment of a host of polytechnics in Europe, Germany, and institutes of technology in the United States, like, for example, MIT in 1861, Stevens Institute in 1870, Georgia Institute of Technology, I think it was in 1885, California Institute of Technology in 1891, and of course elsewhere. These early institutes, which focused on the industrial arts, began by teaching civil engineering and then gradually on other engineering disciplines. Before I discuss the drivers for change, in my opinion, in the next couple of slides, I thought it will be useful to highlight some of the major differences between the world of the past and the world of the future, as highlighted in this slide. I bring to your attention particularly the aspect of in the past that it was linear. Now the future is non-linear. In the past, it was centralist, now it's network, and in the past it was reductionist, now it is holistic. These type of changes will require new approaches to deal with a vastly different set of challenges. All right. Let me take a few minutes to talk about drivers for change. The growing complexity and interdisciplinary foundation of engineering systems. Now, interdisciplinary and interprofessionalisms are topics of growing concern in higher education institutions. Faced with multifaceted problems like climate change and poverty, many researchers and educators have explicitly adopted interdisciplinary outlooks. In healthcare professional schools, for example, and across the developed world, practitioners are being trained for work in interprofessional teams that policymakers hope will be more effective in providing care for complex health issues. Not surprisingly, the conceptual frameworks and curricula used in interdisciplinary and interprofessional programs started to emerge over the past few decades. A variety of different, sometimes even conflicting theoretical viewpoints are taking roots. The second driver for change is the rapid emergence of new technology. Now, emerging technologies are often perceived as capable of changing the status quo. Emerging technologies include a variety of technologies, such as educational technology, information technology, nanotechnology, biotechnology, cognitive science, robotics, artificial intelligence, etc. The third driver is the blurring of boundaries about technical and non-technical disciplines. In my view, blurring arbitrary traditional disciplinary boundaries will foster the development of an improved educational programs and cross-disciplinary research strategy, where research and teaching are blended in a very natural fashion. The globalization as a principal driving force for change, accompanied by increasing global competition. Now, the globalization of the economy demands on the workforce require a different education that enhances the ability of learners to access, assess, adopt, and apply knowledge, to think independently, to exercise appropriate judgment, and to collaborate with others to make sense of new situations. Globalization is not the only factor behind the changes that are affecting education. Nevertheless, globalization has posed many challenges. The nature and complexity of the forces involved in globalization require, in my view, the overhauling of the engineering curricula. The fifth driver is the convergence of biology, engineering, law, etc. Now, if we look or recall a century ago, innovations in physics came together with engineering to produce an astonishing array of new technologies, such as radios, telephones, televisions, planes, radar, nuclear power, computers, GPS systems, the internet, and more. These technologies reshaped our world that we now cannot conceive of life without them. Today, we are on the cusp of a new convergence between biology and engineering, between engineering and geology, and between engineering and medicine, etc. That has the potential to be every bit as revolutionary as the previous one. And finally is the prospective student interests that go well beyond perceived boundary associated with engineering disciplines' traditional roles. Now, the presentation of convergence of education concept is presented in this slide. Now, the general definition of convergence here is that it is the deep integration of knowledge, techniques, and expertise from multiple fields to form new and expanded frameworks for addressing scientific and societal challenges and opportunities. Convergence refers to not only the convergence of expertise across disciplines, but also the convergence of academic, government, industry stakeholders to support scientific investigations and enable rapid transition of the resulting advances. With the continued growth in science and engineering knowledge and the growing evolution towards deep interactions among and between the various academic disciplines, convergence is becoming a real challenge to the education communities. Further details, of course, could be found in the reference given below. Okay, This is really a representation, what I perceive as the evolution of the engineering education over time. If you look at this representation, in the early to mid 20th century, engineering disciplines were operating in silos. If you look at, for example, one can see and observe that the status of disciplines in the 1950s, for example, they were completely disconnected from other disciplines. However, with the progress of time, these disciplines drew closer and overlapped. Let me take an example from my own experience. I would like to highlight the specific educational overlap between mechanical engineering and civil engineering. Now, beyond the basic and mathematical foundation required by all engineering disciplines, if we take mechanical and civil engineering, these two, for example, have their own inevitable educational overlap. This overlap occurs in both undergraduate and postgraduate education. Generally speaking, there is an array of common undergraduate courses within these specific area. Examples: statics, dynamics, strength of materials, also known as mechanics of solids, or structural mechanics, fluid mechanics, basic of finite element method, etc. It is noteworthy here to mention that lecturers need to have an acceptable level of understanding of the applications of their courses in both fields of engineering to ensure the integrity of the engineering education process. It is extremely detrimental to limit the applications in any of the mentioned example courses to just one of these two engineering disciplines. Administration, therefore, and faculty have great responsibility in this regard. Okay, let's get back to the figure here. We can observe that the trend continues expanding as shown in the slide, with the engineering domain itself overlap with other domains. For combined degree, integrating the courses from the very first day of students will enable students to complete their combined degrees in a timely manner. The engineering component, of course, of the combined degree program must be fully accredited, with no core engineering material being lost. Combined degrees programs provide a structural paradigm change in engineering education, which enables significant flexibility in the undergraduate program and produces graduates having great appeal to employers. Now, an example: consider the futures that await graduates with two full undergraduate degrees, say in mechanical engineering and microbiology, or in civil engineering and geology. The example of the changing definition of disciplines, I brought specific one, the mechanical engineering. In the past, mechanical engineering was defined as the branch of engineering that encompasses the generation and application of heat and mechanical power, and the production, design, and use of machines and tools. Now, the definition, however, evolved to mechanical engineering is a discipline that addresses societal concerns through analysis, design, and manufacture of systems at all size scales. The evolving definition or redefinition of mechanical engineering is to ensure that the discipline keep pace with the rapidly changing world. How cross-disciplinary or interdisciplinary and system-based programs offering are will have an impact on the university's placement, among others, as highlighted in this table. Now, interdisciplinary instruction entails the use of and integration of methods and analytical frameworks from more than one academic discipline to examine a theme, issue, question, or topic. Therefore, interdisciplinary education makes use of disciplinary approaches to examine topics, but also pushes beyond by taking insights from a variety of relevant disciplines, synthesizing their contribution to understanding, and then integrating these ideas into a more complete and hopefully coherent framework of analysis. If we leave the research and service element aside for the moment and we concentrate on the teaching, if it is based and delivered in multidisciplinary or cross-disciplinary fashion or not, will have an impact on the placement of the institution classification, classifying it as either being world-class, regional or national, or even local university, as shown in the red fonts in the slides. Having discussed the profession development, I will now outline how we went about developing a system-based education that delivered on producing graduates for today and tomorrow's workplace. Now, in addition to developing a system-based engineering curriculum, institutional requirement could also mandate the implementation of competency-based training approach. This, of course, will require carrying out training need analysis, TNA, to identify jobs and occupation and hence content. As a part of the process, the strategy adopted included a TNA to ensure that the institution meets the national and international requirements fully. It was necessary that all academic programs offered in partnership with the leading UK university meet the requirement of these well-defined sets of competencies and performance metrics that were established by the TNA. These include the progressive development of technical skills, diagnostic skills, i.e. from basic to complex fault finding, fault rectification, modification, or redesign of subsystems, configuration to meet different operation needs and performance criteria, and overall implementation of maintenance strategies. It was accepted by the developing team that the strategic competitive advantage could be achieved by using the right, or I may say, dual-use equipment in its operations. The programs were therefore designed as a holistic system. The industry today, multidimensional, i.e. classified according to various criteria into successive levels or layers of engineering competencies model framework was used. In this model, a bottom-up approach was used to create a framework that encompasses the relevant domains of applicable knowledge, skills, and ability for a complete range of engineering disciplines. For these different engineering competencies, the model framework identifies multiple dimensions where each of these dimensions has unique knowledge, skill, abilities, and attributes that are independent of each other. Application of this model framework enabled heads of department to ensure that and compare the capabilities to various job-specific roles quickly with their expertise mapped to evolving stages of basic skills, advanced or expert levels. Further information could be found in the reference given at the bottom of this slide. Here is an example of a lab for competency training only for the Bachelor of Engineering degree program. As you can see, the set of equipment shown here provide mainly practical training that students get in addition to their academic training during their degree program. Okay, the approach adopted to system-based curriculum. Now, the approach to teaching and learning in the programs was one based on engineering systems combined with engineering practice. The approach inculcated in the students an understanding of the impact and consequences of engineering decisions on issues such as safety management, economics, and environmental pollution, and ethical and moral responsibilities of engineers. Okay, let's now have a look at the heart of the system-based curriculum here. There are 5 essential building blocks for the curriculum. First of all is what I call it problem or project-centered learning. Now, this is an approach in which students tackle a carefully constructed set of problems, generally engineering projects of growing scale and complexity. The problems are so structured that they require the students to acquire particular mathematical and other engineering knowledge, which they do through adjunct educational materials and presentations, but principally through self-directed study. Such projects are often interdisciplinary in nature, involving students from a broad range of engineering specializations. The second building block is what I call the upside-down curriculum. Now, this approach moves materials on engineering applications to the earlier stages of education. Now, why? In order to motivate more strongly the students' interest in the fundamental mathematics and science that can otherwise seem dry and indigestible. The third building block is the mathematics in context. This mainly involves the teaching of engineering mathematics by engineers and presented in an applied setting rather than by mathematicians in a more rigorous proof-oriented style that is ultimately less accessible. The fourth building block is design orientation. Now, many engineering programs place a substantial emphasis on analysis. But creative synthesis, that is design, is a central, perhaps defining activity in engineering and must be central to a curriculum. Engineering students need design experience and in particular should, from an early stage, be working on real problems with real customers and in interdisciplinary teams, such as they would experience in the workplace. The final building block is the combining simulation, TNA, and laboratory. Now, I have already mentioned TNA, so I will not discuss it here again. It is well known that the use of sophisticated simulation has transformed engineering education. Engineers can now design and simulate in silico, reducing the requirement for expensive prototyping and reducing the need for costly facilities. There is, however, a clear limit to this. Students require exposure to the real world of noise, vibration, malfunctioning components, etc. There is no complete substitute for laboratory facilities. As you can see from this slide, the blocks must be all connected through the central theme of safety and sustainability, transferable skills, development and management, and entrepreneurship. The approach to teaching and learning in all of the program is one based on engineering system combined with engineering practice. As I said before, such an approach as well will inculcate in the students the understanding of the impacts and consequences of engineering decisions on issues of safety, management, economics, environment, and the ethical and moral responsibility of engineers to the society. The other aspect of developing a 21st century engineering education based on a system curriculum design is to have an international development approach to the curriculum design at the course level. Now, two universities that do have considerable experience of the engineering systems approach are the University of Melbourne and the Colorado School of Mines, CSM. The former restructured all of its degree programs into what is known as the Melbourne model, allowing it to introduce a systems approach to engineering design. While the Colorado School of Mines pioneered the development of multidisciplinary engineering laboratory studies, MEL for short, for its mechanical, electrical, civil, and environmental engineering students. We engaged with the faculty from both universities of Melbourne and CSM to gain assistance in developing the scope for year 1 and year 2 design and laboratory courses. The former combine lectures with workshops in which the students work in teams to undertake tasks that require creative thinking and an interdisciplinary approach. The laboratory studies module is based on the MEL, which is Colorado School of Mines, modules delivered at the Colorado School of Mines, where students work in teams on tasks that become increasingly more open as the students progress through the years. This approach has been taken as it requires only relatively simple equipment and services, while at the same time develop problem solving, and team working skills. The slide on the left image here shows a class in action at CSM, working in the equivalent of the Year 2 laboratory study module of the designed curriculum. The students are using simple circuitry and signal generators to test certain principles in electronics. Each group of 3 students is assigned its own toolbox for the duration of the module, right image, for which they are responsible and which contains electrical circuit components, simple tools, and power cables. Since the various programs were designed in compliance with the UK Qualification Framework shown in this slide, I therefore thought it is important to display the UK Qualification Framework in this slide. The national qualification frameworks in the United Kingdom define and link the levels and credit values of different qualifications. Pre-university is basically level 3, bachelor degree from level 4 to level 6, and a master degree level 7, and PhD degree level 8, as shown in the slides. This is really the design of 17 separate engineering pathways. On the top, level 3 to level 6, which associated with the UK Qualification Framework, are displayed. Now, the 17 pathway consists of the following. Aeronautical engineering has 2 pathways, mechanical pathway and avionics pathway. Civil engineering has 3 pathways, design pathway, construction management and quantity surveying pathways. Marine engineering had 5 pathways, control engineering, radar and communication engineering, electrical engineering, mechanical engineering, and hull engineering. And the system engineering pathway has 7, system engineering has 7 pathways, power engineering, heating and ventilation, vehicle engineering, ground communication and radar, computer engineering, communication systems, electrical and electronics engineering. Now, the commonality for all disciplines are the cells shown in yellow color, and they represent around 38% of the program content. Discipline specialization are 33% and are shown in the blue color cells, and they represent around 33% of the content, while the discipline specialization is shown, they are shown in the green cell, and they represent 29% of the program. I deliberately highlighted the key modules, Engineering System Design 1 and Engineering System Design 2, and I will really elaborate a little bit on those in the following slide. Details on the development of this program of study could be found in the reference given below. Now, engineering systems design main objective is to really explain the importance and principle of sustainable development and safety, to identify problems and formulate solution strategies, not solutions, solution strategies. Describe how engineers use mathematical models to approximate behavior of a design, and the use of models to evaluate trade-off between alternative designs. Now, if we take, for example, the first year Engineering System Design, or ESD 1, it introduces students to the world of engineering through a mix of design project, interactive workshops, and lectures. It mainly centers on the engineering method, the approach to problem solving and engineering design that makes engineers unique. The subject prepares students for an exciting and rigorous engineering education that will allow them to serve an increasingly complex society. Now, the development of this system-based curriculum need to be supported with enabling tools, many enabling tools. The integrated and innovative laboratory environment, MakeSpace, shown in this slide, is a central tool for the design and delivery success. Now, the environment consisted of modular section that could be easily updated to accommodate new and emerging technology quickly and cost effectively. Now, Due to the fact that this environment could be accessed and operated remotely, completely remotely, the university was able to continue running these courses and this lab even during the COVID lockdown. Now, the various sections of MakeSpace Lab are shown in the slide. This common and shared environment, as I said, support all engineering disciplines and consist of team deliberation corner, which of course could be virtual, software and simulation selection station, rapid prototyping facilities, testing facilities, material selection and measurement section, and manufacturing space. This was designed and for the institution in Oman, MTC. Another earlier version of the MakeSpace is shown here. It features all areas outlined in the previous slides, and you can see it has discussion areas, software resources center, number 2, number 3 is the modeling and simulation, number 4 is prototyping, number 5 is testing, number 6 material selection, and number 7 on the bottom left-hand side is the workshop manufacturing. Now, this is an output and the result of a team project, which is basically a pump, impeller design, and fabrication, reflecting the use of computer-aided design. Here, CATIA was used. It also represents three-dimensional prototyping. It shows the testing and, of course, the creating of the final product. Another example is this multidisciplinary project was to design a house accommodating the culture of this Central Asian country, basically Kazakhstan. Results was really of the design was to suggest 3 options together with the house type building cost, the solar power capital and running costs, the wind power capital and running cost, heat pump capital and running cost, and water treatment capital cost per unit volume, and the running cost per dollar per cubic meter. These are year 1 project design, and really they are focused on the one on the left-hand side, the design of smart building. The one in the middle is the design of solar ship. And the one on the right-hand side is the fuel cell powered bicycle. All right, finally, I would like to share with you the National Academy of Engineering 14 grand challenges for engineering in the 21st century. Now, these 14 challenges are advance personalized learning, make solar energy economical, enhance virtual reality, reverse engineer the brain, engineer better medicines, advance health informatics, restore and improve urban infrastructure, secure cyberspace, provide access to clean water, provide energy from fusion, prevent nuclear terror, manage the nitrogen cycle, develop carbon sequestration method, and engineer the tools for scientific discovery. Now, let me say that all of these challenges cannot be solved without engineers. However, none of them can be solved with engineers alone. Therefore, the engineering profession and engineering discipline must ensure that they are not operated in silo, and to embrace multidisciplinary and cross-disciplinary approach to achieve both success and to be indispensable part of the future challenges as a solver rather than really left behind. Thank you very much.
Thank you very much for that, Prof. Al-Zubaidi. Quite interesting look at engineering education and where engineering is headed, or where the answers that engineers need to be solving. And so this takes us into our question and answer segment. And just a reminder, you may post your questions in the Q&A, and we will acknowledge and read your questions to have Prof respond to them. But first, we have two distinguished professors, or two other distinguished professors who have joined us today, and I'm going to ask that they kick off the Q&A while the rest of you think about it and share your questions. So I'm going to begin with Prof. Chandraban Sharma. He is a professor of electrical engineering at the University of the West Indies, St. Augustine. And Prof, I invite you to share your thoughts, and I think you also have a few questions.
Thank you very much, Sherry. Are you hearing me?
Yes, I can hear you.
Okay. Thank you, Professor Zubaidi. You were in Trinidad, right? Were you?
I was the president
okay.
and acting provost of UTT.
Yeah, UTT. So I just want to make sure it's the right person I'm addressing. Now, being in Trinidad, which was one of the most industrialized islands in the Caribbean, you would have been, and you're based, one of the campus was based in Point Lisas. You would have been exposed to what we call engineering in the Caribbean. One of the issues that I take on with a lot is engineering in the Caribbean relevant to Caribbean issues. And one of the things you find all the time is that many of the methods or the accrediting requirements that you have for engineering programs are requirements that do not help the Caribbean. It presupposes a big GDP that a country has, where a large percentage of that GDP goes for funding engineering programs. In the Caribbean, no government funds any research program. As a matter of fact, they tell you they fund, and when you look at it, is in the hundreds of US dollars to thousands. Also, the industries that you have are mainly foreign industries, and therefore their research arm and research funding goes back to their parent company somewhere in the first world. With that in mind, what do you think should be the relevant engineering undergraduate program for the Caribbean? And I want you to take note of what I assume, and I believe is a fact, having worked outside the industry, is that if we become too specialized in the Caribbean, none of our graduates will find employment. So I think even if you look at an island like St. Lucia, St. Vincent, Grenada, they still need basic engineering requirements, not specialists. Specialists are only required for one-off, and that consultant goes back, and then you just have to maintain what they put in. So with that in mind, that will be my first question. I have other questions, but that is on the chat, so that's okay.
All right. Thank you so much for the question. My presentation is exactly saying you cannot be specialized. You have to have a variety of expertise in the degree program. The students, whether it's Caribbean, whether it is Central Asian, whether it is South African, whether it is Middle Eastern, must be able really to acquire knowledge that he or she needs after they graduate. Because ultimately, it doesn't matter what you provide them in the 4-year or 5-year program. The knowledge is changing, and it is very important that you provide the skill set that enables students to acquire knowledge post-graduation. And certainly, being specialized, maybe it works for the United States, and maybe it's United States alone, but it doesn't work for the rest of the world. You have to be able to know the interface between mechanical, electrical, mechanical, chemical, mechanical, petroleum, otherwise you are really left high and dry. That's number one. Number two is the system engineering approach does not say you don't really deal or tackle discipline-specific problem. You can contextualize the knowledge for that particular class. So contextualization, for example, if air conditioning, well, if if thermodynamics talk about air conditioning, it might not be useful in Alaska, but you need, it might be useful in Alaska. No, sorry, let me go back. Heating, it might be useful in Alaska or Europe. It's not useful in the Caribbean. So you have to convert from discussing heating to air conditioning. So you contextualize the delivery. You are using the same laws of thermodynamics, but you apply them differently. So I agree with you. Highly specialized program is not in the interest of any developing country.
All right, thanks for that, Prof. And I do know that quite a bit of what you shared in terms of the approach is echoed in the ABET accreditation. And so I invite Prof. Lachman, who is from the UWI Mona campus, a professor of electrical and computer engineering, to now join the conversation.
Thank you very much, Sherry-Ann, and thanks Professor Sharman, Professor Sarim, for your presentations, and good to see everybody here. I was trying to get a sort of context of the presentation, you know, in terms of what is it the case that, are you based, Professor Sarim, in University of Bahamas?
I'm currently at the University of Bahamas, yes.
Yes, and is this something that Bahamas is trying to do to try to implement that in their curriculum? Or this is an abstract description of what the concept of what you feel is needed for it?
No, this is something that I've done at 3 universities. The last 2 universities were not in the Caribbean.
And which were these, if I may ask?
In Central Asia, in Kazakhstan, and in the Middle East.
Okay, very fine. Well, that context is helpful. So in the question that just came up in a moment ago about the need for breadth, you know, sort of breadth provided for the interfaces between the engineering disciplines, given the constraint of time, which I think one question earlier addressed, the constraint of time, normally people want to have a 3 to 4 year degree for engineering post high school or K through 12. In order to get enough depth in the discipline to be able to be productive in your chosen or primary field, and the breadth across multiple fields, what is the trade-off there?
Well,
in other words, you may have somebody who is shallow as opposed to being able to innovate.
You have to meet the accreditation requirement in terms of the learning outcome of whatever you're delivering. This is no, I mean, if the programs are not accredited, there are no programs at all. But what I'm trying to emphasize is really, you cannot teach everything that you need to teach or you think it's required in a 3 or 4 years degree program. The important aspect is to teach or convey the skill or the ability of the student to acquire knowledge post-graduation from the university. So basically, this is to me is much important.
I think I agree absolutely with that. We need to equip the students when they graduate from our programs to be able to do continuous learning and to be equipped to do so in an effective and expeditious way as they change their careers or morph into the different disciplines. But what I was concerned about was, you know, within 3 to 4 years, you can do so much to acquire, to be able to satisfy ABET requirements, and also basically equip the students to, in the context of their working environment, to be able to produce. So while I agree that they need to be able to be equipped to learn and be aware of the interfaces, for example, we're working right now on a project to build a video conferencing system, you know, with open source customizations, and you run into the issues of copyright issues or the issue of being sued by Zoom, for example, because they have a patent that for a feature that we're implementing. Those kinds of things clearly need to be in the purview of the students, but you can't teach them all the pieces of it in the various disciplines. So I was just concerned that, and I agree with you that they should be equipped to be able to acquire that knowledge post-graduation.
Just the accreditation requirement forbid institution to overload students.
Exactly.
There is a limit of the number of contact hours and so forth. So I'm talking within the framework of the accreditation requirement. So this has been done within the framework of that.
No, and I think that there are ways to do that effectively, but the depth on each of those, it would be sort of, you offer some breadth, but you have to make sure you have the depth. That's the balance I'm talking about.
Absolutely. Yeah. Otherwise, you get accredited.
Well, I think that you could scrape through accreditation and do a bad job, because accreditation, as you know, is just a set of surveys, right? But you have to be sure that the students be able to produce in their field. And people could pass an exam, for example, and they are very bad engineers. Your curriculum needs to ensure that real learning is happening in the discipline. And so just say accreditation is what you're looking for. That is certainly the signature on the piece of paper, but you have to make sure your program is having very profoundly effective education, teaching and learning. Let me move on to another issue, if I may. The issue
we are talking about professional accreditation, I hope.
I'm talking about ABET.
Yeah, well, I've shown the UK, so I'm talking about IET accreditation or IMAKE accreditation. Go ahead.
What's the difference between ABET and IET?
Well, one is British, the other one is American.
And why do you draw that distinction?
There is considerable difference.
Could you outline some of the differences?
I can't, not online now.
Okay, very good.
But there are differences.
Sounds good. No problem. Thanks. The other question is,
Prof. Lashman, just to give a bit of context, and Prof. Sharma could probably speak better to this than I could, because the University of West Indies, St. Augustine, they are accredited through the UK. One of the key things I know is that the degree is a year longer. And I know Prof. Sharma had asked the question of why should a student take a UK type degree rather than a US degree, as well as an MSc, as one way to cover the breadth of information, doing a US degree and then doing a master's to give you that breadth, so that you cover everything that's required for an accredited program, but you also move on to further studies with an MSc to highlight some of the other competencies that you may not have gained. And I see Prof. Sharma has raised his hand. So I don't know if you want to come in, Prof, before Prof. Al-Sarim responds.
Yeah, since I'm one who has looked at both programs, as a matter of fact, I had developed an accredited agency called CASET, Caribbean Accreditation Council for Engineering and Technology, which was approved by CARICOM. And it was based on the ABET model. And we have been under the IET accreditation model since 60s. If you look at them and really where the issues really lies is the length of time you spend in the program. And it's an unfair thing for students for that, in that whilst the Washington Accord recognized only a 4-year degree as being satisfying one of the criteria for a fully accredited program, what the Washington Accord does not take in recognition is the fact that the students who enter the UK type accreditation program with the UK type qualifications have actually done 1 year more of work already. And the US program, they have done 1 year less of work before they enter. So in terms of what is happening in the program, this is why I asked the question about why you spend this extra year, where CAPE 2, and I'm talking about CAPE 2 in terms of our local qualification, CAPE 2 becomes irrelevant in a system like that. And if you notice what has happened with the UK accrediting agencies, whilst they are retaining this A level, which is the CAPE 2, straight on to CAPE 2, they are telling you that you have not satisfied the full educational requirements to be accredited. And therefore, you must have a matching year. And that's why many programs now, instead of putting on another year, they have a master's program, which they now add on to the program to give them the matching year. But it doesn't give them any more knowledge it just gives them a residence time. However, both programs are recognized as equivalent by the Washington Accord. And that's really where it really lies. And that's where my question came from. Why should a student in the Caribbean do a UK accrediting program when I could do a US program, drop out at Cape One? Many times you could even drop out at O level, get into a US program, spend 4 years and get a fully accredited program and start making money to pay back whatever it is you do. Whilst if the other student who is in the UK program is still crunching away at this program. That's basically it.
Okay, thanks so much for that, Prof. Professor Reem, any additional responses to that?
Well, I wasn't really referring to accreditation, to be honest with you, but since it came, I think this accreditation is very important. You need quality assurance, external quality assurance, and accreditation is an external quality assurance. Also, I guess, you know, if you get ABIT accreditation, you will not be given a pathway to be a chartered engineer, while if you go for IMechE or IET or Institute of Engineering or Royal Aero, you will be able to really be on a pathway to a chartered engineer. So,
actually, that's not true. The programs are equivalent as far as the Washington Code is concerned. That's,
maybe, but the professional bodies, you have to approach them. I don't know.
No, every professional body for registering in that local state, you have to go to a professional body. In the UK, it's the same thing too. That's different to being accredited.
Yeah, it is different. But the degree, let me tell you, for example, I applied for, I hold IMechE fellowship, and I applied for fellowship of the Institute of Engineering Australia. It wasn't a straight swap.
No. What they would tell you is that you have satisfied the educational requirements. However, we have our own requirements to register.
Yeah.
That's what it is.
Yeah.
That's what it is.
Yeah.
But following the questions that the trend there, Professor Zuhairi, having worked in the Caribbean and still in the Caribbean as far as I'm concerned, have you found that one of the issues in the Caribbean is that what we really need are technologists and not engineers?
You know, if you look at the program and competency skill integration, it is recognition that it's very important for developing world that an engineer must be able to do a wider skills. I think without the technical skill, whether HND or HNC level, I think developing world require all of those. You can't really just graduate only a bachelor and master degree. You have to have this level of graduates as well.
Okay, thanks, Prof. There is a question coming in. I don't want to mispronounce. Lilawati Manu Raming in the chat, asking about how can we improve collaboration between engineering practitioners and academia. And I know this is a question that we explored in our very first run webinar, looking at cross-border collaboration. So rather than staying in our silos, doing research or having persons in industry do their research and development, how can we improve that collaboration? All
right. The last time I taught in a classroom was almost 10 years ago, because I started to take executive positions, so I don't have teaching responsibility. But when I developed the program, I interacted directly with colleagues in Melbourne and the Colorado School of Mines in order to work together at the degree program level on developing courses for our programs. So that's number one. And utilize the MOUs signed by the university with other universities and other bodies, whether it is companies and so forth. Many MOUs, I noticed that it's signed and never really activated. It's very, very important. There is a follow-up And these MOUs should be really taken advantage of as well. And of course, personal contacts in conferences, and this is a very good opportunity to make contacts and to establish relationships. It has to come from the person, I think.
Okay, thank you. And I know one of the things that we at the Decree do is, rather than MOUs, we sign cooperation agreements. So we decide at the beginning what we want to cooperate and what exactly it is that we want to work on. I saw a hand raised from one of the attendees. I'm not sure if you wanted to ask a question live. If not, you could raise your hand again. Prof. Hanif, I'm not sure if you had asked all of your questions. You're muted, Prof.
Yeah, just one other question on the question of online learning, as had been more often mentioned in the questions also in the chat. During COVID, for example, or even generally just making education more broadly available, online labs, with augmentation of personal experimentation. Any comments on those matters as we move into the 21st century with mobility and people needing the domestic situation, need to have a job while they're getting their education?
The MakeSpace Lab is an example of a lab that can be completely operated remotely, and you enjoy the deliberation between the team member, identifying the codes that you want to use to really give instructions for the item to be prototype, or using three-dimensional printing. Take this item and run tests using the test rig, or remotely. If you are happy with the results, you analyze the results within the team, discussion with the team. You might need to redesign the piece and continue it again, or if it is satisfied the requirement, then you send it to the manufacturing CNC after you select the material, because it depends, the fluid or the environment it's working under. So this is really, you come into the lab with just an idea what you need to do, and you exit with a product, hardware product. And it is not mechanical only, mechanical, civil, all disciplines, 17 disciplines, aeronautical engineering and so forth. I just gave 2 or 3 examples. I think this type of lab, if you look at universities, their lab is the same from 10, 20 years or 25 years ago, just more equipment in the lab. I haven't seen a newly established lab, even in Australia and New Zealand. It's the same lab with new equipment inserted, new technology inserted. But the conceptual lab, which really revolutionized engineering education, I haven't seen many.
Thank you for those comments.
Okay, all right, thank you. And we definitely can't underscore enough the importance for getting your hands dirty as we balance, the simulations and everything else.
We don't want really to keep the previous centuries, engineers have dirty hand, oily hand. That's not really. Now it is really, it's almost science fiction, to be honest with you.
All right.
I would like to disagree with that a little.
Yes, Prof.
Just imagine I am graduating somebody to go into the power sector. And that person has never seen a transformer, active power transformer, has not put on a circuit breaker, has not seen a wiring going into major power systems. But all he has seen is SCADA systems, microamps. You know how scary that is? That he has never seen a motor actually run. He has never seen a motor starter clamp on, and then you hear this loud noise. And I'm not talking about variable frequency drive and these kind of things where you don't hear anything. What you're actually going to meet outside there in industry, okay? You cannot replace actual hands-on with a simulation. I can understand simulation for your first few years, but coming down to the end, you have to interact on interface with actual equipment.
You see, I need to really remind you what I said in the presentation. There's a clear limit to simulation. It shouldn't require exposure to the real world of noise, vibration, malfunctioning components. There is no substitute for laboratory facilities. I said that in the presentation.
Arif, is that a banks you have there?
Yeah.
They have to get their hands dirty in the lab, right?
Indeed.
So I agree with you. I agree, but I'm talking about the idea in the head. You know, I mean, in the 1950s, 1930s, 1940s, mechanical engineers, at least, I'm not talking about, both of you are electrical engineers. Mechanical engineers, at least, where, you know, oil and stuff, you know, this is really now is different.
We have to fry a transistor, then we have to fry the resistors, burn them up. You know, we have to make.
You should see our capacitor pump, right?
Yeah, exactly.
Okay, all right. Final. I had said final, but we do have one question coming in from one of our participants. Ron Hibbert has asked, how do we involve all stakeholders within the faculty in the business of quality engineering education product production? So not just the lecturers, but getting everybody involved. How do we get everybody involved?
You have to have an effective industrial advisory board at the faculty level and at the program level. I have not worked in a single university at an engineering faculty in which I didn't have a very strong and committed industrial advisory board consisting of not only local industry participation, but also external industry participation. So this allows the programs to appreciate what is the industry requirement, what's the problem faced by industry, and so forth. So this is very, very important. So basically, you are not, you don't become legend in your own mind. So it is very important that you know, you have an input. That's number one. Number two is you have to have a solid quality assurance framework operated within the institution in combination. So you have to be, you know, I mean, it's important also to acquire latest teaching and learning skills as well.
Okay, thank you. I'll go one further because I think the question was referring to within the institution. How do we get everybody involved in the producing that quality product or that quality engineering?
Industrial Advisory Board is within the institution. It is an organ of the institution. It is a committee within the faculty reporting to the dean or whatever. So this is a must, and I think it is, if I'm not mistaken, it is accreditation requirement as well.
Yes, the advisory board is definitely a requirement, and it does involve industry as well as
effective one,
right? Huh? An effective one, right? But yeah, definitely it is important to get even your administrative staff on board, ensuring that they understand the role that everybody plays in producing that quality engineering graduate. So pulling them in to all of the discussions, having them sit on the advisory board as well. So not just your faculty and the industry stakeholders, but having every member of your team be a part of that advisory board. So they get to give their input, share their feedback, because they interact with the engineering students, they interact with engineers. So that is one way to get everybody involved in producing quality engineering graduates. And with that, I want to thank Prof. Al-Zubadi very much for his presentation this afternoon. Thank you also to Professors Sharma and Lachman for joining in on the conversation, and also to our participants and those who asked questions. We do have persons who are watching live on YouTube. We thank you for that. To the SECRE team and to our regional universities networking coordinating team. It has been a good afternoon or morning, depending on where you are. And so we invite you to join us next time, August 13th, we will have presentation from the University of Belize. And so I invite you to stay tuned to be a part of that conversation as well. And with that, have a great afternoon, everyone. Thank you for joining us.
Thanks very much also, Professor Simrim and Sharma and everybody else. Thanks, Sharianne, for arranging.
Okay, thank you so much for being here.